All right, hey everybody. Today we're going to cover one of the most important things, I think, in Calc 3, which is the idea of a directional derivative or the gradient vector. This is going to come up again and again. So understanding the gradient really well is essential in this course. So let's kind of kick this off with the idea of a directional derivative. Okay, so we have a function f of x, y, a function of two variables. We want to find the rate of change of this function at a certain point in a given direction. So we can write it as the vector u, ab, or cosine theta, sine theta, which is a way of making a unit vector going in any direction in the unit circle. So the limit definition of this, what we call this directional derivative, is very much like the idea of a derivative with a function of one variable. So it's the limit of this f of x naught plus ha, y naught plus hb minus f of x naught, y naught over h as h goes to 0. So you can see how this is going to give you the limit of this is going to be the slope in that direction, right, going in the direction AB. But in fact, we have a theorem we can use, so we're not going to have to take any limits at all. And so the theorem is this. The function of x and y that's differentiable, its directional derivative, which we just talked about, is found by taking the unit vector of the direction you want to go in. You take the unit vector u, so AB is a unit vector, has length 1. And so the directional derivative in the direction u for any xy is found by taking the partial derivative with respect to x times a plus the partial derivative with respect to y times b. Now if the vector u is given as cos theta sine theta, then the directional derivative of f of xy becomes partial derivative of f with respect to x of xy cos theta plus partial with respect to y times sine theta. All right, so we're going to see some other notation that we can use, but this is the idea. So let's look at an example. Okay, so let's take the direction u given by this angle theta. So u would be the vector cosine of pi over 6 sine of pi over 6, which is just going to be root 3 over 2 comma 1/2. Now the direction that we're going to go in, okay, so to do this we need to find the partial derivative. We're trying to find the directional derivative, right? So we need to find the partial derivative. So I'm taking the derivative now where I'm treating y as constant, right? So it's going to be 3x squared minus 3y, right? For that second term, x is a constant, but y is the constant. So 3 times y times x, the derivative will be 3y. The last term is completely constant with respect to x, so it's gone. The partial with respect to y is going to be minus 3x, because the first term is constant with respect to y. The second term, the y drops off, so we have minus 3x. And then lastly, we have plus 8y, right? Now, if I want to find the directional derivative of f of, say, 1, 2, what I need to do then is take the partial derivative with respect to x and plug in 1, 2. So it'd be 3 times 1 squared minus 3 times 2, right? Times the cosine of pi over 6, that's root 3 over 2. Now I'm going to take the partial with respect to y at 1, 2. So that's minus 3 times 1 plus 8 times 2 times the 1/2. So working all this stuff out, we have 3 minus 6 times root 3 over 2 plus minus 3, 8, 16 minus 3. That's going to give me 13 times 1/2. Okay, so altogether we've got minus 3 root 2 over 2 plus 13 over 2. We can write that as 13 minus 3 root 2 over 2. Okay. So just to point out that you can actually write the directional derivative as a dot product, in fact. So you could write it as the dot product of u dot with this vector fx, xy, fy, xy, right? A dot product of the directional vector, the directional unit vector. Remember, it's a unit vector, and this other vector here. Now we're going to call this vector here. That's the gradient vector. So this is defined. This gradient vector, this notation we'll be seeing, this upside down triangle of fxy, that's the notation that's used for the gradient of the function. So the first component is the partial derivative with respect to x. The second component is a partial derivative with respect to y. So you can write the directional derivative of f of xy can be written as the gradient of f of xy dotted with the unit vector. You could swap the order, it doesn't matter which order you put the dot product in. But yeah, this is shorthand for a directional derivative. So you want to remember this. Okay, so let's find the directional derivative of this function at f of xy, x squared y to the third minus 4y at the point 2 comma negative 1, okay, in the direction of this vector that's given. Now the first thing we need to do is figure out a unit vector, because we can't do a directional derivative with just any old length vector. The unit vector is going to be v divided by the magnitude of v, okay? Now the magnitude of v, this is 2i plus 5j, right? The magnitude is going to be square root of 4 plus 25. That's root 29. So it's 2 over root 29 I plus 5 over root 29 j. Okay, so we needed that first off. Now we want to find the gradient vector. The gradient of f, this is shorthand we can use because the xy is implied, is given by the partial derivative with respect to x, which is going to be 2x y to the third, right? The first term has x's in, the second term has no x's, so it's constant with respect to x, so it's not going to be in that derivative. The second component, I take the partial derivative with respect to y now. So y is the variable and x is constant. So I'm going to get the 3 coming down, the x squared y squared minus 4y, the derivative of that with respect to y, that's a 4. And now the partial derivative of f of 2 minus 1, it's going to be it's going to be the gradient at this point, which is going to be 2 times 2 times negative 1 to the third, and then 3 times 2 squared negative 1 squared minus 4, dotted with this other vector, 2 over root 29, 5 over root 29. So let's just clean this up. So this is this first vector, 2 times 2 times negative, that's negative 4, and this is going to be 3 times 4. 3 times 4 is 12 minus 4, 8. Negative 4, 8, dot 2 over root 29, comma, 5 over root 29. Okay, so we're going to get 2 times, that's negative 8 over root 29. Everything's going to be over root 29. Negative 8 plus 4, 5 plus another 40. So this is going to be 32 over root 29. So if you have a function of 3 variables, the definition of a gradient vector just extends naturally. We just have a 3-component vector where we have the partial with respect to x, partial with respect to y, and then the partial with respect to z. So no surprises there. And then the directional vector for some function of 3 variables is going to be of a function of x, y, and z is going to be the same thing. It's going to be the gradient of f of x, y, z dotted with this unit vector. But this could have to be, of course, a three-dimensional unit vector, right? But that's this is exactly, and if you were dealing with higher dimensions for some reason, then it's going to just extend the same exact way. Remember, you have to use a unit vector when this dot product. You can't just use any length vector. Okay, let's take a look at this example. F of x, y, z is x times sine of y, z. Let's start with finding the gradient, okay? And so the first component, we're going to treat x as the variable, and so the derivative sine yz is just a coefficient. So sine yz is going to be what's left over. When we treat y as a variable, the derivative of, we have to be careful about all this, so x times the cosine of yz times the derivative of yz. Remember, treating y as the variable, which means we'll get a z. I'll just put the z out front. And then if we're going to be treating z as a variable, the same thing. It's going to be x times the cosine of yz, but this time the chain rule gives me a y. I'm going to make room for the y there. Now, if I wanted to find, for example, let's find the gradient of f at the point 1, 3, 0. Okay, so this is just going to be, I'm going to be plugging in 1 for x, 3 for y, and 0 for z. Any place the 0 pops in the sines and cosines, so that's going to be zeroing those out. The sine of 0 is 0. The cosine of 0 is 1, so z times x, that's 0 times 1, that's another 0. And then the last one, we have 1 times 3 times 1, that's a 3. So if I wanted to find the directional derivative of f of x, y, let's see, if we want to do at the point 1, 3, 0 in the direction of v, which goes in the direction 1 to negative 1, okay, we need to make this into a unit vector. The unit vector is going to be 1 to negative 1, but we have to divide by its magnitude, which is going to be 1 plus 4 plus 1. That's the square root of 6, right? So the unit vector is the vector 1 over root 6, 2 over root 6, and then negative 1 over root 6. So the directional derivative is going to be the dot product. It's going to be the 0, 0, 3 dotted with 1 over root 6, 2 over root 6, and negative 1 over root 6. It turns out this is just going to give us negative 3 over root 6. That's all there is to it because of those zeros, right? So here's a theorem that actually follows from our understanding of the directional derivative as a dot product. If you have a differentiable function of 2 or 3 variables, the maximum value that the directional derivative can ever take is going to be actually the magnitude of the directional derivative, it's the magnitude of the gradient itself at whatever point you're at. And it will occur in the direction that is parallel to the gradient vector. If you remember, if you're finding the dot product of 2 vectors, right? It's going to be the magnitude of the first vector times the magnitude of the second times the cosine of the angle between them. And the cosine is maximized when they actually have a 0 angle between them. So you're going to get a maximum dot product when this unit vector is pointing in the direction of the gradient vector, right? Then you have the product of their magnitudes times 1. And that's going to be the most you can ever get because the cosine is maximized at 1. It follows, of course, that the minimum value of the directional derivative is going to be in the opposite direction of the gradient vector. And its the minimum value of the directional derivative is the negative of the magnitude of the gradient. Okay, so let's just see what this looks like. If we're at the point 2, 0, and the function we're looking at is x e to the y, we want to know what's the direction towards this other point q at 12, 2. So first off, let's find the gradient, right? The gradient of f is going to be found, it's e to the y, and then the derivative with respect to y would still be just x e to the y. The gradient of f at the point 2, 0 is, I'm going to plug in 2 and 0, so e to the 0 is 1, and 2 times e to the 1, that's a 2. Okay, so the direction, I'll first do the directional derivative, I'll do the displacement vector, right, from p to q, and that's going to be a change of 10 in the x component and a change of 2 in the y component. But the unit vector is going to be 1 over, let's see, that's the square root of 104. That's 100 plus 4 times the 10, 2 vector. And so the directional derivative in the direction of u of f at the point 2, 0 is going to be 1, 2 dotted with this, you know what I'm going to do is I'm going to put the, I'm going to just do the 1 over root 104 out front first, and then the 10, 2 dot 1, 2. I realize I could have actually factored some stuff. I could have made this other vector a little smaller, but it's all right. I'm not going to be too concerned with that. So it's 1 over root 104, which, okay, fine. So I can factor out a 4 of that. It's going to be 2 root 6? 26 times 4, it's 104. Times this vector, times, what do we have? 10 times 1 is 10, plus 2 times 2 is 4, 14. So that's going to be 14 divided by 2. 7 over root 26. Okay, but I want to know in what direction does the maximum rate of change occur? The maximum rate of change at the point 2, 0 is going to be in the direction 1, 2. And the maximum rate of change is the square root of 5. And you could work this out just in a decimal that 7 over root 26 is going to be less than root 5. You can trust me. Yeah, so that's just this fact about the gradient is the big takeaway about gradients that you need to really know. Gradients tell you the direction where the maximum rate of change occurs, and it tells you what is the maximum rate of change. Okay, both of those pieces of information are encoded into the gradient vector. Okay, so let's say the function t of x, y, z gives the temperature in a room. It's 80 over 1 plus x squared plus 2y squared plus 3z squared. Now, we are at this point 1, 2, 1, 1, negative 2. We want to know in what direction, in 3 dimensions, does the temperature increase fastest. Okay, so this is going to be another, just a matter of finding the gradient. Now, what I'm going to do is I'm actually going to write t as 80 times 1 plus x squared plus 2y squared plus 3z squared to the negative 1. It's going to be a lot easier to take the derivative writing it that way. So I'm going to find the gradient of t, and I might as well just pull the 80 out front for the purposes of this. Now, the first component is going to be the derivative with respect to x. So I'm going to have negative 1 plus x squared plus 2y squared plus 3z squared to the negative 2 power. And then I'm going to multiply this by the derivative with respect to x. And this is a polynomial, and so the only term that's going to be constant with respect to x is the x term, which is going to give me a 2x. Now, I'm going to do the same thing for the others, and so I'm going to have negative 1 plus x squared plus 2y squared plus 3z squared times the derivative with respect to y, which is going to be 4y. And because all three of the other terms are all constant with respect to y. And then the last one, negative 1 plus x squared plus 2y squared plus 3z squared. And then we have 3 times 2 is 6z. Now this is all very messy looking, but you notice that you can actually take this, sorry, I wasn't putting the negative 2's on there. We can actually write this as 80 over 1 plus x squared plus 2y squared plus 3z squared times the vector 2x, that's squared, 2x, comma, 4y, comma, 6z. And I'm going to now evaluate this. The gradient of t at the point 1, 1, negative 2, it's going to be negative 80 over this thing. So I'm going to put 1 plus 1 squared, which is a 1, plus 2 times 1 squared, which is a 2, plus 3 times negative 2 squared. 3 times 2 squared is 4 times 3. That's going to be a 12. That's squared. And then this vector is going to be, let's see, 2 times 1 is 2, 4 times 1 is 4, and 6 times negative 2 is negative 12. Okay, still cleaning this up a little bit. Down below we have 1 plus 1, it's 2 plus 2. That's going to be a 16. 16 squared is 128. it's 120. No, it's 20. It's 256. Of course. So we have 256 down there. So minus 80 over 256 is, and then we've got this vector. Actually, I'm gonna take the 2 out of that vector, and we have 1, 2, negative 6. So I'm going to clean this up just a teeny bit because some stuff cancels. We have negative 5/8 times the vector 1, 2, negative 6. Which, okay, let's put it all in terms of one single vector. I'm done playing games with that. It's negative 5/8, negative 10/8, which is going to actually be 5/4, and then we've got negative 6 times that. So it's going to be 3 times, that's going to be a positive 15 over 4. That's the direction where the temperature increases the fastest, but the rate of change is the magnitude of that. And so the magnitude of the gradient at the point 1, 1, negative 2 is going to be 5/8 times the magnitude of this other vector, 1, 2, 6, negative 6, whatever, is 5/8 times the square root of 1 plus 4 plus 36. That's 36. That's 41. That's 5 root 41 over 8. So that's the rate of change. That's in degrees per meter in the direction negative 5 over 8, negative 5 over 4, and 15/4. Now, I guess you could, if you're just interested in the direction of 1, 2, negative 6 is fine. Like, you don't have to put the direction, the magnitude of the direction vector doesn't matter. If we're just asking the direction, you can just give the direction vector scaled at any amount you want. So might as well just drop off the constant. But I should keep the sign. It's still negative going in that direction. If I'm not keeping the sign in there, then I'm pointing in the opposite direction. That's a no-no. Okay. Yeah, and so that's the rate of change. All right. Okay, so if you have a level surface, say you have f of x, y, z equals k, and we want to find at the point, say, x sub 0, y sub 0, z sub 0, we want to find the tangent plane to this surface. The equation is going to be a little bit messy looking. Well, it's just long. It's actually quite as a pattern to it. But so it's going to be f. You'll remember this from the equation of a plane. It's going to use the fx, the partial derivative with respect to x at x0, y sub 0, z sub 0 times x minus x sub 0 plus the partial derivative with respect to y at x sub 0, y sub 0, z sub 0 times the y minus y sub 0 plus capital F, the partial derivative with respect to z at x sub 0, y sub 0, z sub 0 times z minus z sub 0 equals 0. So that's going to be it. Now I guess you could actually write this as it's the directional derivative of f at x sub 0, y sub 0, z sub 0 times the vector. You could do r minus r naught equals 0. Like that is fine. You could write it like that as a shorthand. And you can see that's exactly like what you see. So it turns out the gradient at that point is actually pointing in the direction of the normal vector, right? So the normal line that's passing through this point, x sub 0, y sub 0, z sub 0, can be found, and I'm going to give you the symmetric equations, x minus x sub 0 over partial f with respect to x at the point x sub 0, y sub 0, z sub 0 equals y minus y sub 0 over capital F y, right, the partial with respect to y of x sub 0, y sub 0, z sub 0 equals z minus z sub 0 over capital F. That's the partial with respect to z at x sub 0, y sub 0, z sub 0. So there's the symmetric equations of the normal line. You can find tangent planes, tangent lines if you have a level surface. Okay, so let's consider this. We have an ellipsoid, and we want to find the tangent plane at this point, -2, 1, -3. Okay, so what we have here is this is what I'm calling f, and so the gradient of f is given by the partial derivative with respect to x, which is going to be 4 times x to the third over 4, which actually ends up being just x to the third. The partial with respect to y is just a 2y, and then we have. This is not an ellipsoid. Hold on a second. Let's hold on a second. This should be x squared, not x to the fourth. It was something. It wasn't an ellipsoid. Let's just stick with an ellipsoid. So, okay, back to this. So it's going to be 2/4, which is 1/2 x over 2. That's the partial derivative with respect to x. Partial derivative with respect to y is going to be 2y. Partial derivative with respect to z is going to be 2z over 9. The 3 doesn't actually do anything for us. 3 doesn't really matter. So we're going to then, so the whole thing then, the equation of the tangent plane is found by taking this, we take the gradient at the point -2, 1, -3, right, which is, so we have -2 over 2, that's -1. 2 times 1 is, it's a 2. And then if you put a -3, you have -6 over 9, that's going to be -2 over 3. The tangent plane is going to be found by taking this, -1, 2, -2/3, dotted with x minus -2, which is going to be +2, y minus 1, and z minus a -3, which is actually z plus 3, equals 0. That's the tangent plane, which we can write out in a full-on equation, just without the vectors, it would be negative x plus 2 times y minus 1 minus 2/3 z plus 3 equals 0. Yeah, there's the tangent plane. So another application of the gradient vector, that's going to be the normal vector to a tangent plane. Okay, now we could turn the question around and think of the well, what is going to be, if you have an ellipse, at what point on the ellipse is the tangent plane going to be parallel to this other plane? All right, so we can just find the gradient vector, right? The gradient of f is going to be 3 times 2 is 6x, 6 times 2 is 12y, and z that's a 2z. That's the gradient, and the normal vector of this this other plane is the vector 1, 2, 3, right? So we want to find some value where we so we want the gradient to be parallel to this other. Sorry, we want the tangent plane to be parallel. That means the gradient is going in the same direction as that. So in order for that to be the case, we need to find a point on this ellipse. Now we need to, I'm going to use a constant c to help me out here. So if the gradient is equal to that, I'm going to say that I want to set some constant times 6x times 12y times 2z equal to 1, 2, 3. What I'm trying to do here is, actually, let's forget about the constant for the moment. Okay, so I can solve for x, y, and z, but I just want the two vectors to be in the same direction. I need to make sure that the point is on the ellipse. That's the thing. So if I was just to solve this equation, first off, I could get x is 1/6, right? That's the way you'd solve the first part. Y is going to be 12 times y, so it's going to be also 1/6. And then z, it says 2/3, that's going to be 3/2. Now, if we check, this point is not on the ellipse. But, so I want to find the c such that the point c over 6, c over 6, and 3c over 6 is on the ellipse. Okay, so as long as the two vectors are parallel to each other, we've gotten what we want. Do you see what I mean? I'm going to plug this into the equation of ellipse to solve it for c. So it's 3 times c over 6 squared plus 6 times c over 6 squared plus 3c over 6 squared equals 1. So this is going to be 3c squared over, why do I have 3/2, not 3/6? Whoops. 3/2. Okay, so we have 3c over 36, 3c squared over 36, plus 6c squared over 36, plus that's going to be 9c squared over 4 equals 1. And solving this. So you know what I want to do actually with these 2/3. I'm actually going to multiply all of these by I'm going to find some constant such that at some point c comma c comma, I'm multiplying each of these by 6 in order to get rid of the denominator, just to keep things a little cleaner. So we have 3/2 times 6, that's going to be 3 times 6, it's going to be 9c. I want to find a value of c such that c times 9c is on the ellipse. So the idea now is I'm going to be plugging in this point into the equation, and I'm going to see what it solves to give me, right? So I'm going to put 3 times c squared plus 6 times c squared plus, that's going to be 81 c squared equals 1, right? So we've got 81 plus 6, that's going to be 90 c squared equals 1. C is going to be, c squared is 1 over 90. So c is going to be, well, it's going to come out to be 1 over, I guess, 3 square root of 10 plus or minus the square root of 10. So this is going to be these points. So the point would be so either plus or minus 1 over 3 root 10, 1 over 3 root 10, and then 9 over that, which is going to be 3 over root 10. This point is on the ellipse. We can check it and make sure. Those points are on the ellipse, and based on what we've done, we know that the gradient vector is going to be parallel to the vector 1, 2, 3 at those points. You can double check that and see that that is indeed the case. So this is you should have this in mind thinking about gradients. So if we're at any point, think about topological maps, because here's an example of one where we have contour lines. We have this river. So the river is at the low point, right? So if you're at, say, this point here, if you want, where is the direction of the gradient? It's going to be going uphill in the direction that's actually going to end up being perpendicular to the gradient line. And so we could sort of make an approximate path to the steepest point. We can kind of go up here at this point here. It looks like I would go off in slightly that direction to go steep uphill. From here, looks like you would have to go in this direction. Here we'd go this. So what I'm doing is tracing a path to, I'm kind of walking the steepest path possible to get to the highest point. That's what this exercise does. Actually, and you can realize that going in the opposite direction is going downhill the fastest. So here we can go downhill, and we're going to meet up with the river. Now one thing that you have here is if you're at at some point in the direction of the gradient, if you go in either, I didn't draw it very well, the 90-degree angle in either direction should have a 0 gradient. Okay, the gradient should be 0 if you turn 90 degrees in either of those directions. That's going to give you, you'd be walking on level ground. And actually, it makes total sense if you think about the level curve. If I was a little person and I was walking along this line and I followed this line, right, I would not be going uphill nor downhill. I would just be staying along a level path. And so at any point we find ourselves in this world, right? If you just find the gradient, that's pointing uphill the steepest direction possible. Okay, that's the really important thing to grasp for this section, is the idea of the gradient as the direction of steepest incline. And with that, I'm gonna close it all off. Okay, bye.